Hi everyone, thank you for joining us today for this month's scientific webinar. So as you'll be aware in these webinar series, what we do is we present application of SimSib and also PBPK and present it to a wider audience. So often these are publications which have been published, and we just like to promote that science as well. So as usual, the session will run with the presenter giving their talk. If you can remain muted during the presentation, that would be great. And then we'll spend some time at the end to take any questions. So our speaker today is Bridget Morse from Eli Lilly, and she has a PharmD from Butler University as well as PhD from the University of Buffalo. And as many of you may know, she works at Eli Lilly, and she's an expert in PBPK modeling, PK modeling, transporters and drug-drug interactions, and currently holds the position of Senior Director in Global PK/PD and Scientific Lead of Quantitative Clinical Pharmacology. So you may be aware of her paper with her colleague earlier this year in DMD, looking at the impact of OATP1B1 and looking at the interactions, drug-drug interactions utilizing PBPK. So I won't go into much about these key learnings because I think Bridget's going to do a good job at explaining some of these during the presentation. But I'd just like to thank Bridget for agreeing to speak to us today, and please present your presentation.
Thank you, Ollie, for that introduction. We'll get started then. So as you could tell by the title, today we're going to go through some mechanistic exploration underlying the distinct PK that we see during OATP substrate drug interactions. So first, let's look at comparing and contrasting what substrate PK looks like during a drug interaction, assessing metabolism versus those on OATP1-mediated uptake. So as you can see here in the two graphs and tables, this is clinical data from the effect of our prototypical CYP3A inhibitor, clarithromycin, on our index CYP3A substrate midazolam, given when midazolam is given both IV and orally. And so you can see from the parameters following IV administration, the clearance goes down with clarithromycin administration, and the half-life goes up. And the volume of distribution, as assessed by non-compartmental analysis, or NCA, does not change. And then following oral administration, the clearance over F goes down even further because there is an increase in bioavailability as well as a decrease in clearance. The half-life similarly goes up again, similar to that with IV administration. And the Cmax increases again because bioavailability and clearance are both changing. I do want to point out that with this metabolic DDI, the Cmax ratio is smaller still than the change in the AUC. So there's about a 6 to 7-fold increase in the AUC, or decrease in clearance over F, and about a 3-fold increase in Cmax. So now let's compare that to our clinical drug interactions in which we assess effective and prototypical OATP inhibitor, IV rifampin, on some commonly administered OATP1B substrates, atorvastatin in the top and rosuvastatin in the bottom. And so you can see with both of these OATP substrates, clearance over F goes down, again, about 6-fold for atorvastatin, about 3-fold for rosuvastatin. Interestingly, though, the VD over F, again, determined by NCA, also goes down, and it goes down even further than clearance. And so while bioavailability may be involved in these drug interactions, this implies that volume is changing more so than clearance during these drug interactions. And so as such, the half-life actually decreases, as you can see, particularly with atorvastatin. It actually decreases the plasma concentrations below that of control, which is something we don't see with metabolic DDIs, as you can tell on the left-hand side of the slide. And then there is also an increase in Cmax with these drug interactions. Now, conversely to those on metabolic DDIs, the Cmax is actually, the ratio is bigger than the change in the AUC. And so again, this is with an IV administered inhibitor, such that we don't expect any involvement of intestinal transporters in this drug interaction. And so that is not likely the explanation for that increase in Cmax greater than the AUC. So you can see some very distinct PK differences in a drug interaction assessing effect on an uptake transporter using rifampin, again, as our OATP1B inhibitor versus those on a metabolic DDI. So now let's look at the definitions of clearance and volume as it pertains to OATP substrates. And so as you can see, and this is probably very familiar to many of you, we can define the clearance according to the extended clearance model for compounds that are actively taken up. And so for these compounds, the liver structure looks similar to this, in which we assume a barrier between the extracellular and intracellular water and potentially asymmetric distribution between the two, as well as metabolic clearance or biliary clearance from inside the cell. And so we can then define the intrinsic clearance based upon these processes and incorporate that into the well-stirred model to define the clearance based upon these parameters. We can also include these parameters then in defining the volume of distribution according to the extended clearance model. So a very classic definition for volume is the volume of the plasma times the sum of the volume of the tissues times the Kp. We can incorporate transporters by then multiplying that by the Kpuu, which can then be accumulation due to active uptake. And so the Kpuu is defined here, and you can see this is embedded in both the definition of clearance as well as in volume, such that changes in OATP-mediated function should affect both. And so we do expect OATP inhibition to decrease clearance and volume. However, the decrease in volume should be limited to the contribution of the apparent liver volume. As you can see by this depiction of a typical PBPK model, there are other organs involved in BDSS, which are not expected to be affected by OATP inhibition. And so just addressing some limitations to assessing actual changes in clearance and volume in these clinical studies from which we have data. For almost all of the clinical studies we have, the OATP substrate is administered orally. And so that limits our assessment of clearance change to that oral clearance change. It also limits the assessment of volume of distribution to that MDZ over S, so terminal volume, which is actually a calculated volume based upon clearance and lambda Z, and not a physiologic volume. Additionally, in order to assess rifampin as a somewhat specific OATP inhibitor, we are limited to a single dose of rifampin for OATP inhibition because dosing it to steady state, as many of you know, will cause strong CYP3 induction as well as induction of other enzymes and transporters to some extent. This is a limitation because rifampin has a relatively short half-life of about 3 to 4 hours, and so that can be shorter than many of the substrates that are being assessed. And then finally, our prototypical OATP1B substrates are acid, and they often have complex disposition. And so many of them undergo enterohepatic circulation. As many of you know, acids tend to form an acyl glucuronide, which can then get excreted into the bile, cleaved in the intestine, and then reabsorbed as parent. Or the acids may go through biliary excretion as intact drug and get reabsorbed depending on their passive permeability. Additionally, many of our most commonly administered OATP1B substrates, the statins, undergo reversible metabolism through their lactone. And so the lactone species often are unstable in different physiologic pHs and therefore can reversibly go back to the active acid forms and contribute to their disposition. And so many of our clinical OATP substrates are impacted by one or both of these processes. However, alternatively, drug interaction simulations with PBPK models can actually allow direct calculation of clearance and volume using simulated plasma and tissue data, such that we can actually explore the role of volume of distribution in these observed clinical DDIs. And so the objectives of our work were first to provide a complete literature review of single-dose rifampin, as well as a specific change in an OATP1B1, so genetic variants on the effects of the PK parameters for various clinical OATP1B substrates of varying disposition. And so using DIDB, we collected clinical DDI data assessing the effect of rifampin 600 milligrams single dose as a precipitant given both IV or orally. And then furthermore, the substrates were binned according to their OATP and CYP3A substrate status. And then to address the potential caveats related to the use of single-dose rifampin and OATP1B substrate disposition that may impede our interpretation from those clinical studies, we performed simulations with PBPK models to compare calculated PK parameters using necropsy specifically to assess the change in volume of distribution with those determined by non-compartmental analysis. And so the first aim of this was to address CYP3A induction by single dose of rifampin to evaluate the potential magnitude of that and how that might affect OATP1B substrate PK. And then furthermore, use this model to simulate with substrate models for both hypothetical OATP1B substrates of varying complexity, and then with complex OATP1B substrate models, Atorvastatin and Pitavastatin, that have been validated to reproduce the clinical PK of those two compounds and include those the complex disposition that we discussed previously. And so to the first aim of our work, the paper includes a very long table of all of the clinical drug interactions assessing a single dose of 600 milligram rifampin. I'm just showing a subset here so that you can see the range of data that exists in the literature. And so first, when we look at substrates that are both OATP and CYP3A substrates, you can see the AUC ratio for many of these can range from very small to very large, as well as the Cmax ratio. And for many of these, the Cmax ratio does indeed increase more so than the AUC ratio, almost most of these cases, I would say, but not always. And then few papers actually report the volume of distribution change. However, the couple that did report a decrease. And then in these two cases, it does appear that the change in volume was greater than the change in the clearance, or the inverse of the AUC ratio. And then for many of these substrates, a single dose of rifampin led to a decrease in the half-life. Again, these are CYP3A and OATP substrates. Again, some of them, or most of them, but not all of them. And I do want to point out so that we did in these tables try to point out which substrates do have complicated disposition, so evidence for biliary excretion in EHC and or reversible metabolism. And so you'll see the hashtag for the compounds that do have complicating disposition. And so then we also looked at the effect of rifampin, or the reported DDIs, on the effect of a single dose on CYP3A substrates. And so there were fewer of these reported in the literature. As you can see, as expected, for compounds that are not OATP substrates, you don't see significant differences in the AUC or the Cmax ratio. However, still for some of these CYP3A substrates, they still report a significant decrease in the half-life. And so for some of them, but not all of them, and particularly for midazolam. So there were a handful of studies looking at a single dose of rifampin on midazolam. Midazolam has a relatively short half-life, and so the interval over which it was assessed was different in each of these studies. And so we noticed that the longer the interval, then the shorter the half-life ratio actually became. So the studies which could actually assess midazolam past 12 hours actually started to show a decrease in the half-life of midazolam. And so then looking at non-CYP3A substrates, so OATP substrates that are cleared alternatively. So again, since they're not OATP substrates, many of these are cleared via the bile and or have a role of reversible metabolism in their PK. Again, a range of AUC ratios and Cmax ratios, some of which, again, we see a Cmax ratio greater than the AUC ratio, particularly if you can see for ezetimibe and rosuvastatin. Again, we do have one compound that actually reported a significant increase in half-life. This was the only one that was an increase in half-life of greater than twofold out of all the studies that we found. It is actually a CYP2C8 substrate. However, for many of these other compounds, again, depending on the study and depending on the interval over which they were assessed, many of them report a significant decrease in the substrate half-life. And then for substrates, compounds that were not substrates, so either OATP or CYP3A, there were a few that still assessed a single 600 milligram dose of rifampin. An increase in AUC was observed for compounds like dabigatran, which we presume to be due to OATP inhibition. And Cmax changes were similar to AUC changes in these studies, with no change in the half-life for these non-substrates. And then we also compared this to the effect of SLCO1 pharmacogenetics on the substrate PK. And so in this table is the ratio of the parameter values between subjects that are wild type versus subjects that are homozygous variant. Variants over the wild type. That's the ratio for the AUC and the Cmax and the half-life. And so you can see smaller changes in the AUC and Cmax, of course, right? 1B1 is only one of the OATPs present in the liver. And so we know these are going to be smaller changes than that of rifampin, which will inhibit 1B1 and 1B3. Interestingly, in these, the AUC and Cmax ratio were more comparable for most of these studies, and half-life actually did not seem to change, either increase or decrease, with a specific change in OATP1B. OATP1B1 function. Again, many of these substrates have complicating disposition. And so as we go into our hypothetical models, we'll see the role of these disposition factors in interpreting these PK. So just to sum up then the clinical data on OATP1B substrate PK, we see a range of AUC and Cmax ratios reported with OATP1B substrates with both rifampin and with the variant effects. With rifampin, however, often the Cmax ratio is greater than an AUC ratio, whereas that with pharmacogenetic effects, generally the Cmax ratio is about similar to the AUC ratio. Almost no DDIs with a single dose rifampin report an increase in substrate half-life, even though the AUC ratio can go up past tenfold. It doesn't appear that specifically decreased OATP1B activity with the variants affects OATP1B substrate half-life either. Alternatively, many single-dose rifampin DDIs report a decrease in substrate half-life, and this seemed to be true for CYP3A substrates, regardless of their OATP1B substrate status. So that was particularly interesting. And also for substrates with evidence of biliary clearance loss, EHC, and/or reversible metabolism. And then notably, we found that very few object drugs were not CYP3A substrates, nor had evidence of EHC. So very few OATP1B substrates have rather straightforward disposition. And so we also thought this was another advantage of the PBPK modeling, that we can assess OATP substrate models with varying complexity and somewhat distinguish the complicating effects of rifampin versus the complicating effects of substrate disposition on the results that we actually see in the clinic. And so then getting into the PBPK modeling that we performed, first what we did was an assessment of CYP3A induction following a single dose of rifampin. And we did this using midazolam as a verification. And then we built hypothetical OATP1B substrate models with both low and high extraction. So we built 14 in total. Models 1 through 7 were low ER, and models 8 through 14 were high ER. And so on the left here are in the dashed lines the perturbations that we assessed on the substrate disposition through these various models, and you can also see it in the table here. So we had substrates with relatively simple disposition that were not OATP substrates, did not have enterohepatic cycling or biliary clearance, and did not have any renal clearance. We did assess the effect of having high or low passive diffusion on the DDIs, however, in that case. We also then added, instead of non-specific metabolism to those substrate models, we put metabolism on CYP3A to see how that would affect the DDIs, again, assessing both high and low passive diffusion. And then keeping passive diffusion high, we also assessed the effect of adding EHC. And so we did this through the formation of a glucuronide. So we added half of the clearance on UGT, which formed a glucuronide metabolite, which was then completely converted to the parent in the intestine and completely reabsorbed. So complete recirculation of about half of the metabolic clearance. And so then we also added renal clearance, and then we assessed having both renal clearance and EHC together on what that DDI would look like. So these are the low ER models labeled 1 through 7. And then we made analogous models with high extraction ratio. And when we did so, we kept the liver KPUU, the renal clearance, at least for the low and the high ER models, and all the perturbations and the VDSS maintained, such that that would not confound any of our results. And so using these models, we then compared a single 600 milligram dose of rifampin using the rifampin model that I'll describe shortly, compared that to continuous and selective OATP1B inhibition, so mimicked by just a tenfold decrease in the OATP1B intrinsic clearance. So just assuming perhaps we do have an inhibitor that could cause continuous and selective OATP1B inhibition. And so then again is assessing the effect of rifampin on those models, and then also with clinical OATP1B substrate models to compare with actual clinical data. We used an Atorvastatin model that we published a few years ago, and I'll briefly explain that. And then we also validated a Pitavastatin model herein, and I'll explain that as we get to it. And so then just looking at the assessment and verification of CYP3A induction by a single dose of rifampin, we used the SimCYP rifampin multiple dose model. We modified it slightly, decreasing the IV clearance to account for autoinduction. So I think it was maybe a 10 to 15% decrease in the clearance, not too different. And then we added into the multiple dose model the OATP1B inhibition that was on the rifampin single dose model. And so we fixed the Ki at 16 nanomolar for both OATP1B1 and 1B3. And we fixed it at these values because this is what we had in the rifampin model that we had previously used for our Atorvastatin verification. And we have also, which I'm not showing in this presentation, but we have verified this model also against available rifampin data against coproporphyrin using the coproporphyrin PBPK model that was published by Pfizer. And so these are realistic values, we believe, for the KIs. As you can see, then we just validated the ability of the model to reproduce rifampin PK following both IV and oral administration from the available clinical studies. There is a little bit of variability in the studies, as you know, is typical of clinical data, but in general, we felt that the model was accurately reproducing rifampin single dose 600 milligram PK. And then to assess the effect of induction, we looked at, again, studies reporting a single dose of 600 milligrams rifampin on midazolam. And so there were 4 studies that we found, all report minimal effect on midazolam Cmax and AUC, which is not surprising. However, 2 of them did indicate a decrease in midazolam half-life. Totosian et al., which is the microdosing study, actually provided a sufficient profile out to 24 hours that we could actually assess the effect or the performance of the model for reproducing the plasma concentration profile of rifampin with a single dose, midazolam with a single dose of rifampin. And you can see here the model did indeed, with the multiple dose induction parameters that were already in the rifampin multiple dose model, reproduce the effect of rifampin and the decrease in half-life observed in midazolam when given with a single dose of rifampin. And so then we also output the simulated effect of rifampin on CYP3A enzyme. And we compared that also with the percent OATP inhibition, which we would expect given a single dose of rifampin. And we just calculated this again with the observed or the simulated rifampin plasma concentrations and the KIs that we put into the model. And so interestingly, as you can see, so the induction of CYP3A reaches about 300%, it's about 3 times baseline. That happens about 16 hours following rifampin administration. That's also approximately the same time that unbound rifampin concentrations fall below the OATP1B Ki, such that it appears we have somewhat of a biphasic DDI occurring temporally, in that at the beginning of the profile, we have predominantly OATP inhibition. That effect is lost due to the short half-life of rifampin, and that's actually when induction may be predominant. And as you can imagine, that causes some relatively interesting PK profiles on certain substrates, which we'll show with our hypothetical substrate models. Okay, so the next four slides are going to look relatively similar. They are assessing relatively simple, both low ER and high ER OATP models, and then complex OATP substrate models. So I'll just orient you to the outlay of the next 4 slides. So in the PK profiles, we've got both an effective rifampin, which is shown in the dotted line, and then also effective simulated continuously decreased OATP1B activity. And then here in the with the squares are the PK parameter ratios that we calculated using NCA following administration of rifampin in the squares, or following OATP1B inhibition, so decreased OATP activity in the circles. And then here I've also output just the baseline PK. So the baseline PK is in the solid line here. For each of the models, just so that you can see what the half-life and the clearance look like in the absence of rifampin, and how that actually impacts the drug interactions. And so the first thing I think that's, and I should orient you also to this vertical line. So that's that 16-hour mark that I discussed previously, at which rifampin concentrations start to fall below the Ki, and induction is also reaching maximum. And so you can see with each of the profiles that the dotted and dashed lines do not overlay, and they start to diverge actually after we approach that vertical line. And so you can then look at the PK profiles. And so we did all of these to mimic the clinical scenario. We gave both the OATP substrates orally as well as rifampin orally. We also assessed the effect of rifampin on IV simulated substrates because we could, and because that allowed us then to calculate the change in F as well as systemic parameters. You can see here continuous OATP inhibition resulted in a decrease in clearance by about tenfold, which is how much we decreased the OATP1B activity by for these low ER substrate models. However, that was quite different from the effect of rifampin for all of these models. OATP inhibition did decrease the volume as determined by NCA, but not as much as it did the clearance. However, you can see distinctly, it looks like rifampin had a similar effect on clearance and volume. And so now with the substrate given orally, we might look at this profile and suspect that it's actually bioavailability that's decreased, since these two are changing similarly. However, since these are low ER compounds, as you can see here, clearance is very low, FH is already very high. There's not much room for F to increase. And so that is not actually the explanation for why these two things look similar for rifampin. It's actually due to the fact that the substrate half-life, even with very simple models, is very long compared to rifampin, such that we're losing the effect during the assessment period. And so then we can, if we look finally at the substrate half-life, this is where there's a lot of divergence between OATP1B inhibition versus rifampin, and also between models. So you can see if we had an inhibitor that could continuously and selectively inhibit OATP, we would expect an increase in half-life. Again, these compounds are completely cleared by the liver. Whereas the volume is not only involving the liver. So we do expect an increase in half-life, not a decrease in half-life. However, for rifampin, even for relatively simple models, we actually don't predict an increase in half-life. And actually with a CYP3A substrate that has high passive diffusion, such as model 3, we actually predict a significantly decrease in the substrate half-life. And you can see this crossing to below the control concentrations that we pointed out previously with atorvastatin that can be observed with this model. And so although model 4 is also a CYP3A substrate, given the passive diffusion in this model is relatively low compared to the metabolism, you don't see the effect of increased metabolism in the plasma. If we were to look at the liver, we would see a change in the liver profile. However, for this compound with low passive diffusion, you don't actually observe that. And then finally, I do just want to point out, so the change in volume of distribution. And so with OATP1B, continuous OATP1B inhibition, we could calculate the change in volume of, in steady state volume of distribution, which is the true physiologic volume of distribution, by adding up the Kp values, the Kpu values of the liver, and calculating that actually using kind of a simulated necropsy. And you can see that that indeed decreased as expected with OATP inhibition, but it did not cross the volume which was related to the rest of the body. So in these models, the liver was approximately about half of the total volume. And so you can see it decreased almost the entire liver volume, but did not decrease it to more so than that physiologic. However, if we look at using NCA to get the effect of rifampin on BZ, you can see the decrease in volume is artificially low, more so than is actually physiologically possible. And so just pointing out then that even with these simple models, this decrease in volume is simply not physiologically possible. but likely due to artifacts due to the short half-life of rifampin, as well as CYP3A4 induction on CYP3A substrates. And so then these are similar models with both high and low passive diffusion CYP3A non-CYP3A substrates, but have high extraction. And so you can see, just looking at the profiles, comparing the dotted and the dashed lines, and also looking at the change in the parameters, rifampin is more similar to continuous OATP1B inhibition, primarily due to the short half-life of these compounds. So the half-life is about 2 hours, so shorter actually than rifampin, and also the primary change in F for both of the compounds. So since we've got high concentrations of rifampin during the first pass, we actually have quite a similar effect as that compared to OATP1B inhibition. The main difference here is that rifampin still is not predicted to increase substrate half-life, whereas OATP1B inhibition is. And then same thing, I just wanted to point out again, when using NCA to interpret the change in volume following rifampin, we get decreases in volume which are not physiologically possible, even though when we can calculate the true change in VDSS with OATP1B inhibition, using both NCA actually, or the simulated necropsy calculated value, that does not exceed that of the rest of the body. And then looking at some more complex models, these are, again, the low extraction models. This is just the base model that I showed 2 slides ago. And then we added EHC, added renal clearance, and then combined both EHC and renal clearance. And you can see, again, half-life is quite long for all of these substrates, particularly when we add EHC. As expected, the half-life increases significantly compared to the base model. And so, again, comparing the dotted and the dashed lines from these substrates, particularly the ones that are completely cleared by the liver, again, we see some divergence, whereas it's closer for models 6 and 7 because the change, even with OATP1B inhibition or decreased OATP activity, is lesser because there is a non-hepatic clearance route. And so you can see then, again, you can just see that here, right? Less of the change in clearance with these models that include some renal clearance. Again, since these are low ER models, F is not changing. I don't think I pointed this out before, but with the low ER models, the Cmax is increasing more so than F. That actually is due to a decrease in volume of distribution. And so that's related at least to the increases in Cmax greater than AUC that we do see with the clinical data. And so what's interesting, though, what we see here, particularly with model 7 with OATP1B inhibition, this is the only case in which we actually predict a decrease in half-life with continuous and selective OATP1B inhibition. And so we think this is due to the fact that EHC is interrupted, as well as the fact that there is a non-hepatic clearance route that actually leads to a decrease in half-life. However, looking again at the effect of rifampin, still with none of these models is a single dose of rifampin reported to or expected to decrease the half-life of the substrate. And then finally, just looking at our high ER models with complex distribution, and these may actually be more like some of our clinical OATP substrates. OATP substrates tend to have relatively high extraction, particularly if they're meant to get to the liver, and many of them do have complicated distribution. Again, so this is our base model that we just showed 2 slides ago for simple disposition, OATP inhibition versus rifampin administration don't diverge too much. And you can see that from the parameters over here as well. Again, what seems to be different between the models and between rifampin versus OATP inhibition is actually the effect of the perturbation on half-life. So for a high ER model, which does not include renal clearance, but does include enterohepatic circulation, actually this is one case in which OATP inhibition is not expected to increase the half-life, and rifampin is actually expected to decrease the half-life, as you can see in this picture. And then that's similar to model 14. OATP inhibition, again, is actually expected to decrease the half-life somewhat when we include both EHC and renal clearance. And rifampin is also expected to cause a somewhat distinct profile in which the half-life decreases and then actually returns to normal. So very distinct profiles that we see with these models with rifampin administration and complex disposition. So then just some quick conclusions before we move to the more complex clinical substrate models, conclusions on our hypothetical models. So a single dose of rifampin seems to differ from continuous OATP1B inhibition if we had an inhibitor that did that, particularly for OATP1B substrates with long half-life because of the short half-life of rifampin. Selective continuous OATP1B inhibition is predicted to result in an increase in substrate half-life because for compounds that are cleared primarily by the liver, OATP1B inhibition is expected to affect clearance more so than volume. The only exception for that is for models that undergo enterohepatic cycling that have renal clearance, in which we do actually predict OATP1B inhibition to decrease the half-life. However, this is not because volume is changing more so than clearance. It is because of the complicated disposition of those particular substrates. And then finally, single dose rifampin is never predicted to increase the substrate half-life. So similar to what we observed in our clinical, in our review of the clinical data, actually rifampin is predicted to decrease the half-life due to CYP3A induction and interruption of enterohepatic circulation. And then just looking at the reported effects in volume. So volume as assessed by NCA often results in a decrease in VZ or VZ over F that is equal to or more so than clearance or clearance over F for these substrates. But we can see when compared to VDSS, what is actually calculated from tissue data, these might actually be artifacts. And then just looking at the two clinical OATP substrate models that we built to see if we could reproduce the observed effect. Both Atorvastatin and Pitavastatin have DDI, more than one DDI study assessing the effect of single dose 600 milligram rifampin. And so we built or used previously built complicated PBPK models that included the lactones in these substrate models. And so just briefly, for those of you that are not familiar with this paper, with the Atorvastatin PBPK model, we included formation of the lactone in the stomach because in vitro we have determined that atorvastatin is quite unstable and forms the lactone actually rather quickly at gastric pH. And so this lactone is actually absorbed. It can undergo CYP3A metabolism, but in the plasma it is unstable and goes actually back to atorvastatin. And so atorvastatin is one example of a high extraction substrate of CYP3A. But plasma atorvastatin is a result of both absorbed atorvastatin, so that which passes through the portal circulation and doesn't get extracted, and also absorbed atorvastatin lactone, which undergoes reversible metabolism in the plasma. And so actually when we built this SimCyP model at the time, this acidic conversion was not a capability. It is now, but in the version 17 that we built it, it was not. So we had to dose atorvastatin, figure out how much of the dose was converted in the lactone, and then give that much lactone. So we actually had two workspaces that we had to combine using Phoenix at the end to get the resulting profiles. And while that was a little tedious, it actually was helpful because I'll show you, we could actually look at the effect of rifampin on each of those two components that contribute to atorvastatin in the plasma. And so just to show you that the atorvastatin PBPK model was verified to reproduce the dose dependence in the clearance and the Cmax that we see, the nonlinearity in atorvastatin PK, as well as the effect of an OATP inhibitor, rifampin, as well as that with itraconazole. So it was verified with basically all the clinical data that existed for atorvastatin at the time. And so what we did then is we simulated this atorvastatin DDI with rifampin with two different atorvastatin models, the complex model that we just described, and also a simpler model that is more analogous to our model 7 here that had a high extraction ratio, but was a CYP3A substrate. And so when we simulated with this model, with the rifampin PBPK model that we built, you can see we do reproduce an increase in the AUC and Cmax. However, the half-life is predicted to remain the same, which is not what's reported. However, when we use this more complicated model, because of the reversible metabolism, we are better able to accurately reflect the observations. And so, as I mentioned, with this model, we actually had to dose atorvastatin in atorvastatin lactone. And so we actually had a result when we simulated with both itraconazole rifampin on that absorbed as atorvastatin acid and on that absorbed as lactone and backformed to atorvastatin. And so the contribution of the DDI is actually a total of these things, and it's quite interesting to look at how they get combined. So when we look at absorbed atorvastatin acid, just looking at the blue line here, that's the placebo. You can see what's interesting, using the predicted volume as expected for an acid, the half-life actually is predicted to be quite short. The long half-life of atorvastatin, I think actually is a result of that reversible metabolism from the lactone. So the disposition alone of these two species actually look quite different. And then as expected, actually, itraconazole, because atorvastatin is uptake rate limited, we don't see a huge effect on that absorbed as atorvastatin acid. Where we see the effect is that absorbed from atorvastatin lactone, because the lactone is actually the sensitive CYP3A substrate. However, we see the big effect of rifampin on the absorbed atorvastatin acid, with little effect actually on that absorbed from lactone, because this is not undergoing first pass extraction. And so then the observed AUC that we see with both of these inhibitors is actually the composite of absorbed atorvastatin and that from lactone, such that you get this distinct profile and predicted decrease in the half-life. And so then briefly, I'll just go through how we validated the pitavastatin PBPK model for simulation with the rifampin PBPK model. And so pitavastatin, we've actually assessed, it is actually quite stable at gastric pH. So we did not have to include gastric conversion of the lactone. Instead, pitavastatin gets absorbed and forms the lactone in the liver via UGT1A3 primarily, which is supported by the in vitro data. Pitavastatin lactone can then enter the systemic circulation, and then it back converts to pitavastatin. And so again, pitavastatin is an example of a moderate ER OATP substrate, not a substrate of CYP3A, conversely to atorvastatin. But plasma pitavastatin, again, is a result of absorbed pitavastatin, reversible metabolism of pitavastatin lactone in the plasma, and then additionally, enterohepatic recirculation of pitavastatin. And so there's a significant amount of preclinical data indicating that pitavastatin is found intact in the vial, quite a bit of it. However, the FA of pitavastatin is high, such that this is not actually a clearance mechanism, but it will still affect the plasma profile. And so this is just a brief description of the verification of this model. So we do have IV data for pitavastatin. And so we use that IV clearance to determine the active uptake and the scaling factors. We did, of course, have to include scaling factors from the in vitro data. We input the active and the passive as measured in-house, and then added the scaling factors on the active. The fractions transported by the various OATPs were determined as determined in vitro by a publication from Pfizer, and that's cited in the paper if you'd like to look. The FMs in the liver for 2C9 and UGT1A3 were fixed to reproduce the human C14 study. And so these are the results of the human C14 study. And so you can see, we do see collect the hydroxy metabolites in the excreta. And so that's how we determine the FM for CYP2C9. And then the rest was fixed to UGT. The BDSS of pitavastatin acid, actually, we fixed to that as predicted by method 2, which actually predicted a rather short half-life for pitavastatin. Its observed half-life is about 12 hours, but the predicted half-life was about 2 using this. However, we, as I pointed out with the atorvastatin, this long half-life seems to be a result of the lactone reversible metabolism as well as the enterohepatic circulation. Then once we had the hepatic parameters fixed, we fixed the FA-FG to about 1 as reported in the absolute bioavailability study. And then we incorporated the reversible metabolism of the lactone. So we fixed the reversible metabolism in the plasma from in vitro stability data. And so this was not a clearance mechanism for pitavastatin lactone, so it had to have a clearance mechanism. And so we put it actually into the bile where it actually formed pitavastatin. So from this human C14 study, actually the primary route of excretion appears to be pitavastatin in the feces. However, since pitavastatin is highly absorbed, we don't think that's actually due to intact excretion of pitavastatin itself, but actually pitavastatin glucuronide or lactone excretion into the intestine where it's probably unstable. And so we did consider the plasma PK as well as the mass balance to validate this model. And as you can see here, we compiled all the data we had for pitavastatin and pitavastatin lactone. Pitavastatin and the lactone PK appear to be linear, and so these are all dose normalized to 2 milligrams of pitavastatin. You can see they overlay the profiles quite nicely. And then, as we did with atorvastatin, we simulated the rifampin DDI using a rather simple pitavastatin model, and then that incorporating the complex mechanisms we just discussed. And so you can see, assuming or not including this complex disposition does not appear to reproduce the concentration profiles for pitavastatin in the presence of rifampin, in the absence or presence of rifampin, honestly. However, we were able to reproduce the plasma profiles closely to the observations with this complicated model in the rifampin model described. And then finally, these are the PK parameters of those 2 DDIs simulations that I just showed you. And we also simulated the effective SLC01 genotype. So I just want to point out a couple things. So the observed Cmax ratio for atorvastatin is actually greater than the AUC ratio, and our model was able to capture that, as well as the decrease in half-life and decrease in volume more so than the change in clearance, actually, which are reported. And then similarly to pitavastatin, actually, the Cmax and AUC ratio, the observed numbers are more similar, as were these model simulations. However, the model did predict the decrease in half-life and decrease in volume over F as reported. And then similarly, we predicted the effective SLC01 variant genotype on atorvastatin and pitavastatin, and these are the results here. And we did this just assuming the decrease in 1B1 activity, as is input in SimCip with people that have this variant, are homozygous variant. And so you can see doing so decreased or increased the Cmax and the AUC if pitavastatin without a predicted meaningful change in the half-life as reported, and the same thing for atorvastatin. So this lack of change in the half-life due to the SLC01 genotype appears to be related to the complex disposition of pitavastatin and atorvastatin, particularly that reversible lactone metabolism, and as you can see here. Okay, and then finally, just the conclusions of this current work, the overall conclusions. So complexities related to both rifampin and OATP1B substrate disposition seem to complicate interpretation of studies using a single dose of rifampin as an OATP inhibitor. This is due to CYP3A induction, short rifampin half-life, and enterohepatic circulation, meaning that the system is actually quite dynamic over this time period, even following single doses. PBPK modeling in this work helped us understanding the role of change in volume of distribution, because that could be incorporated on these distinct OATP1B substrate profiles that we observed. So again, OATP1B inhibition is expected to decrease VDSS, but by at most the contribution of liver volume. And certain changes in apparent volume, as determined by NCA, do not necessarily reflect those in true VDSS when we actually have the tissue data as we did in these simulations. And then finally, the current PBPK modeling, including mechanistic change in VDSS, could reproduce the distinct change in the OATP1B substrate PK following single dose rifampin and SLCO pharmacogenomics, if we include the complexities related to rifampin as well as those on our the substrate disposition for our complex OATP1B clinical substrates. With that, I just want to thank the QCP group at Lilly, particularly Pooja, our postdoc, who has now moved on, but who performed all the simulations here, and then also Ali and Gabby for the invitation and for the help during this webinar. And with that, I will take any questions.
Thank you, Bridget. That was brilliant. Are there any questions? Please feel free to either raise your hand or unmute yourself and fire away with any questions. Otherwise, you can use the chat, obviously. I mean, to me, it was really great incorporating all those complexities. Sometimes you're like, where do you start? But that was really interesting how you broke things down into the different components. I guess one question obviously is how you move on and apply this within your kind of routine work, particularly in light of the use of rifampin. How do you utilize that?
Yeah, I think we still can use the rifampin data. We just need a model that accounts for the short half-life as well as the induction that happens, later on in the profile. And then we can actually understand and tease out, right, the effect of OATP1B inhibition by rifampin and get the Ki values as long as we are using models that accurately capture the complexities of rifampin, as well as with the substrates that we know can be quite complicated in the clinic. So I think, yeah, I guess I would say the static calculations using NCA, our interpretation of those is not very helpful. We need PBPK models that incorporate these things in order to really interpret what's happening and actually get Ki values for OATP, right, which is what we really are using rifampin data for.
Yeah, I agree. Are there any other questions online? Yeah, Dan, do you want to unmute yourself?
Yeah, hi, can you hear me?
Yep.
Yeah, thanks. Really interesting talk. My question's a bit of a niche one, just on pitavastatin, where I always had it in my mind that that's an MRP2 substrate, and so it's efflux directly into the gut. But then I think you mentioned, Bridget, that it's possibly the metabolites being excreted into the gut. So did I pick that correctly? And any further thoughts or details you have on that, please? Thank you.
Yeah, actually, I believe it's both. However, since pitavastatin has, let's go back to the depiction. Since pitavastatin has a high FA, its excretion into the bile via MRP2 is not going to be a clearance mechanism because it is completely reabsorbed. It will, as the model at least predicts, it will increase the half-life, that recirculation. However, the fact that pitavastatin via the mass balance study is completely or mostly recovered in the feces as intact, and that can happen via numerous ways for various drugs, particularly acids. Actually, the model suggests that that's due to secretion of, it could be the glucuronide. Of course, we know that UGT forms the glucuronide, which then quickly goes to the lactone or the lactone into the GI, which then the lactone particularly is quite unstable at physiologic pH, so blood pH or intestinal pH, which could go back to pitavastatin. So actually, the model could be incorporated MRP2 efflux of both pitavastatin and or the metabolite, which could be then undergo reversible metabolism in the gut back to pitavastatin. Does that make sense, Dan?
Yeah, thanks. That's really helpful and interesting. But yeah, really great talk. Thank you.
If there's no more questions, this obviously.
And yeah, I will just say, I know since we can't use rifampin anymore, cyclosporin is our clinical OATP1B substrate. So we did go through this exercise with a cyclosporin model as well and validated that. And we're hoping to get that published by the end of the year. So we are
brilliant.
For that. Yeah.
That's good. That's yeah, I was wondering a bit about that, but thank you for clarifying that. Okay. Thank you, Bridget. I really appreciate your time and that great presentation. If you wouldn't mind just moving on to the last slide before we go, just to highlight that we have another webinar. Next one's near the end of November. I know there's a lot of kind of SimCit webinars coming up, but this one is from Ming-Liang Tang from FDA, and she's going to be looking at PBPK modeling to predict DDI interactions between omeprazole and extended release nifedipine. So this is related to PhD DDIs. Please register in the usual way for that. Okay, thank you everyone. Thanks for your time, and thanks again to Bridget for that great presentation today.
Thank you.
Take care.